Okay, if you have problems, I can mostly see you past the bright lights here. So just raise your hand and we'll get somebody to help you out. All right, so the first part of this, we're going to talk about a little bit of background where Spark came from. Okay, we have some guy you're having difficulty with.
Wi-Fi is like 2K a second.
Okay, so we're having Wi-Fi issues. Anybody else having Wi-Fi problems? All right, we're going to have to get somebody. We're going to have to get somebody on that. Andy, can we get somebody to give us a hand with the Wi-Fi?
Yes. Can you raise your hand again if you're having problems? All right. Okay. And the problem. Okay. Is anybody actually having a problem getting onto the Wi-Fi? Raise your hand if you are having a problem getting onto the Wi-Fi. Okay, so it's all just slow for people. Okay, great. All right, I'll go ask.
All right, well, we'll keep going. We're going to try to get that figured out in the background. All right, so a little bit of background. My name is Brian Clapper. I'll show you a little bit of background on myself in a little bit, but we're going to talk just, I don't know, 10, 15 minutes about the background of Spark, where it came from, who Databricks is, that sort of thing, and then we'll get into the more technical stuff. Right, so we've got Databricks is the company commercializing offerings around Spark, founded just about 2 years ago by the people who created Apache Spark. Okay, and the original team for Spark came from the AMP lab at UC Berkeley. They're well funded. They've raised just under $50 million in 2 rounds of VC funding, and they have about 55 employees. Right, if you want to work there, apparently they're hiring. I don't work for Databricks, so I can't tell you what they're hiring for, but there are Databricks people around here. And they do a lot of level 2 and level 3 support. So now why do I bring this up? Because people who are working in enterprise development shops, one of the things that we're all concerned about is, hey, if I use this thing, can I get support, right? Well, yes, the answer is you can. Okay, and one thing to note is that the Databricks team is actively involved in more than just support, right? Their team actually actively develops Spark, and they've contributed more than 75% of the code that has been added to Spark in the past year. So they're not just doing support, they're not just there to make money off helping us use Spark, but they're actually actively contributing, maintaining, and enhancing Spark and moving it forward. All right, now here's our agenda for the day. This is a bit fluid, so we'll do our best to stick with this. But this morning before lunch will be around noon. This morning we're going to give you a brief history. That's sort of what we're going through now. We're going to talk about RDDs, which are the fundamental building block inside Spark. We're going to take a look at the Databricks UI, the Databricks notepad and or notebook and everything that goes in around that. This is what we'll be using to do the labs and to do some exploration of Spark. Then we're going to do a lab where you get a chance to play with Spark in a guided manner. We're not just going to throw you into a Scala REPL and say, okay, start typing. Right? So the nice thing about this particular approach is it's a guided lab. All right, and then right before lunch, we're going to start talking about some of the transformations and actions, the things that you can do with data that you're pulling through Spark. All right, and then after lunch, we will continue with that, and you can see the rest of the. We're going to be discussing. We have many labs, much time for you to play with Spark. We're going to talk about data frames, which is a newer and more performant API for interacting with data through Spark. We're going to talk about the various Spark UIs that the Databricks offerings provide for you to help diagnose what's going on with a Spark application that's running inside a cluster. We'll talk about some of the resource managers. We'll talk about memory persistence and caching of data, which is a way you can speed up your transforms. And then toward the end of the day, we will talk some about Spark streaming, and we'll try to wrap up with, if we have time left, we'll try to wrap up with another set of labs. So, the point of all this is that there's plenty of hands-on. It's not just going to be me standing up here talking at you. So it's good you have your laptops open, because you will be using them. Somebody asked me before, should I have downloaded anything and installed anything before this class? And the answer is, you're certainly welcome to install Spark, although don't do it right now, obviously. But it's not necessary for this class, right? We're going to be using the Databricks notebooks to do all of our work. So as long as Wi-Fi allows everybody to get out to the web-based notebooks that are out there, that's fine. You do not need to do any work on your personal machine for the purpose of this class. I will probably occasionally show you what it looks like to use Spark locally in a local REPL as well, but you don't need to be doing that in here. All right, so if you borrowed your daughter's laptop and don't want to install Spark on that, like I sometimes do, you're good to go. All right.
If it does turn out that the Wi-Fi is a problem when we use our Spark that's installed on our Wi-Fi?
You certainly can, but this is geared around the online offering. The question was, if the Wi-Fi turns out not to be fixable, can you use the local Spark on your machine? You can. You'll have to work a little harder because this stuff is all geared toward doing it online. But at the moment, I wouldn't worry too much about that. We've got people working hard to try to get the Wi-Fi fixed, so we're hoping to get that fixed. Worst case, we can all, I guess, turn on our phones, right?
No, there's no internet connection.
Well, I think I have one. So, okay. Some people can go through my phone, I guess. All right. This is a rather large slide deck. Okay, so we're going to spend some deep amount of time on some of the slides. Some of them I'm going to skim through, and I might adjust some of this depending on the time. I mean, if people have a lot of questions, that will tend to slow us down, and we'll cover less material, and I might have to skip some slides. Regarding Q&A, we'd like to try to keep that to a minimum during class, not because we don't think your questions are valuable, but because questions tend to send us down tangents and into the weeds, and there's a lot of material to cover. So we'd like to try to keep, if you have questions, please make sure that they're on point and tied to what we're covering at that moment. If there are more detailed questions that we don't get to, not only are Databricks people hanging around here, but all of us are going to hang around after 5 o'clock. There'll be like a half hour, 45 minutes, where you can come up and beat us up with questions, and we'll be happy to sit here and answer them. So this is just because there's too much material to cover for us to be going off on questions. Okay, we're going to have 2 anonymous surveys. Many of you already done the pre-class survey. I'm going to show you some of the results of that survey up here so that we all get to know one another. And then toward the end, we're going to have a brief post-class survey, and then you guys will be able to look at the results. And then lunch, I think I already mentioned this. We're going to take an hour for lunch at around noon. All right, and I will be disappearing at lunch. So if you're holding your questions till lunch, a lot of us are going to disappear. We have a few things we got to do, and then we'll be back at 1 o'clock. And we're going to try to have 2 breaks, but if you find yourself absolutely needing a break and I'm on a roll and I'm not stopping, just raise your hand and say, can we stop for a break? Sometimes I forget, so you're welcome to remind me. All right, so this is a little bit of background on me. There are some links up here if you want to read, but basically what you should take out of this is I'm a developer, like many of you in here. I tend to come at this stuff from a developer's perspective. I'm learning Spark, which is not something you do in a day, right? From a developer's perspective, not from a manager or an executive perspective, or even from a DevOps guy's perspective. I learn it through code. As we'll see in a few minutes, the demographics of the group in here, many of you are the same way. I hope that what that means is that I'm going to help bring a developer's perspective to this as opposed to a data scientist perspective. If you want a data scientist perspective, I'm probably not your guy. If you want a developer guy's perspective, that's a different story. I have a pretty strong development background. I run a Scala user group in Philadelphia. I've been using Scala for, I don't know, about 6 years now, 7 years. But I program in Python, Ruby, loads of different languages. I spent 9 years doing nothing but Java. All right, the reason I mention in particular Scala, Python, and Java, a lot of people think, my God, if I'm going to use Spark, I have to know Scala. I'm not ready to know Scala. Well, the answer is you don't, right? Most of Spark is written in Scala with some Java, but there are interfaces, as you probably know from a lot of the talks, there are APIs for interacting with it through Scala, through Python, through R, and through SQL, right? So, and Java as well. So you can use the language of choice. Now, we're not going to be using Java in here primarily because the REPLs and the online tools do not support Java at the moment. I understand the Java team at Oracle is actually working on an interactive shell for Java. I'll believe it when I see it. It took them long enough to get lambdas in there, but let's keep our fingers crossed. And presumably when a REPL is available for Java, it'll be pretty quickly available for use within Spark. In here, the examples are largely going to be Scala and Python. But don't worry too much. Most of it's guided. If you don't understand Scala, if you've never used Python, it's going to be okay. Most of the code is cut and paste within an environment, so you don't have to panic that we're going to be throwing deep functional programming at you. That's not going to happen. Okay, so again, feel free to look me up. Feel free to contact me if you wish, offline. I do tend to answer email. I get a lot of it, but I do answer it if people contact me. All right, so this is a bit of a summary of the pre-class survey. About half of you filled out this survey. So that's enough of a sample size that we can get an idea of who's in the room here. Most of you are developers, right? We have some administrators and ops people in here. There are some people who self-identified as management or executive, but it's mostly data scientists and developers in here. Okay, which is good for me because that's my perspective. All right, so look around. Most of the people you're looking at are developers like you, right? Hence the large number of beards in here. All right, where did you guys all come from? Well, as isn't really a surprise, the significant number are here on the West Coast. But the other big pocket of development is the East Coast. So about a quarter of the people in here said they're coming from the East Coast. So I would assume most of that's New York or the Northeast Corridor, which is where I'm from. And then we have sprinklings of people from elsewhere in California, elsewhere on the West, and 10% of you are actually here from Asia. Okay, so it's a somewhat diverse group, but kind of clustered the way our whole industry is clustered here in the U.S., right, on the two coasts. All right, little bit, I'm not going to spend too much time on this, but feel free to look through here. This identifies the industries that everybody comes from. Lots of us from the IT side of things, but science and tech and banking and finance, which is no surprise to anybody, is well represented in here. And then telecom, lots of telecom interest in big data. All right, again, there's more detail here if you want it. All right, most everybody in here is new to Spark, right? No prior Spark training for the bulk of everybody. So you're all on pretty much the same footing, which is good. And the same is true with hands-on experience. Some of you have been playing around with Spark for about a month or so, some for about a week, some like not at all. Almost half of the people in here have almost no experience with Spark. There's like 4% of you out here who claim you've been using it for more than a month. I may ask who you are because we may draft you as TAs. All right, and another set of demographics on the Spark usage life cycle. Again, I'm not going to really go into this, but again, most everybody is in the reading stage. We're still learning about this. We're still trying to figure it out. Okay, so that's why you're here, right? That's why we're in an intro class. All right, and then there's some demographics here on programming experience, which are kind of hard to read, but I'm not going to go deeply into them. It doesn't surprise me that the bulk of people, when asked about Scala, said, I don't really know that much about Scala, or I'm just starting to get into it. There's what I would call a kind of unreasonable fear of Scala in the Java community. As somebody who has used it for a long time and who teaches a Scala class, I can tell you most of that fear is somewhat unfounded, but it is there. So we're not going to try to shove Scala down your throat, as I said. A few more of you are, the bottom graph is Python, right? So a few more people in here are familiar with Python. There is no reason that you should feel like Python is a second-class language when it comes to Spark. If you want to do the work in Python, do the work in Python. Okay, by all means, use the language that they support, use the language that you're comfortable with. Loads and loads of data and numerical analysis these days is done in Python. So if that's your preferred language, by all means use it. Some of the examples will be Python here, and some of them will be Spark. We tried to mix them up. Scala, sorry. Okay, this is just more of the same, although here's, you know what? I misidentified that previous slide. That was actually Java. So a fair amount of Java experience. Here's the Python experience. Again, roughly similar layout for the Python, and a bunch of SQL guys in here. So once again, you can interact with Spark using a lot of your current SQL knowledge. So that may be the way you want to go at it, and again, that's perfectly fine. Right, and then R, which has just been introduced. I will tell you right up front, I do not know R very well at all. I am not going to be talking about R in here. But if you use and like R, then 1.4 now provides support for R, and you should feel encouraged, to use it. All right, and again, I'm going to try to skim through this a little bit, but this is mostly what kind of big data experience do people have, and as you can see, if you can read any of the categories up here, it's all over the map. Okay, so we're coming from a whole bunch of different perspectives. Probably the largest component here are people using HDFS. Good news there is that you get to keep using HDFS, right? Spark does not make HDFS go away. All right, so the focus of this class will primarily be development, which correlates quite nicely to the demographics of all of you sitting out there. We'll talk a little bit about some administration and ops stuff, but we've really de-emphasized that in here. That tends to be confusing when you're starting out trying to learn Spark. We're not going to worry too much about, gee, how do I start up a cluster? How do I figure out where all this stuff is running? How do I figure out if it's running quickly? At the moment, what we're concerned about is that you feel comfortable writing code that lets you manipulate data in Spark, right? The ops stuff comes later. Okay, so we're not going to worry too heavily about that. We'll touch on it briefly here and there. We're going to talk a little bit about the architecture, but once again, if your goal is to come at this as a programmer and actually try to get some stuff done, architecture initially is sort of a secondary thing, right? Let's make sure you understand how to use it, and then you can start to worry about how to optimize it. So again, we'll talk about architecture a little bit, but mostly we're concerned about let's make sure you feel comfortable experimenting with and using the tool set. And we'll talk a little bit about use cases, but again, I'm going to say this for a third time, we really want to make sure that you're comfortable walking away from here feeling like I can dive into Spark and start writing some stuff and playing with some data, because it's really the best way to learn how to use anything. Okay, so now here's a little bit more background, right? We've had a bunch of, this particular slide refers to these as the storage wars and the processing wars, right? And the point here, you'll note that it says NoSQL battles then and compute battles now. The point of this slide is that, a few years ago, everybody was all over NoSQL. There's arguments about NoSQL versus SQL. There's arguments about which NoSQL is better. And the contention that we're making here is that the NoSQL battles have been pretty much decided. And I'll show you some information in a minute that supports that assertion. The compute battles are what's happening right now. We figured out how we're going to store this data. What we haven't figured out is what is the best way to process this data. And so that's where Spark comes into play, and that's mostly what we're going to be talking about here. How does Spark fit in with the existing ecosystem of compute tools? What does it replace, if anything? What does it augment? What does it allow you to do better? And how can you mix it in with what you're already doing? Okay, so the red here, and I'll show you another slide in a moment that details this in a little bit more, I find a little more readable, but the basic idea here is that if it's red, it won, okay? So everybody's still using relational databases. I know I have plenty of clients who want to use relational databases. I have plenty of clients who use both relational and NoSQL databases. So NoSQL has not beaten relational databases. We all heard the hype 5 years ago, and it's all turned out to be kind of nonsense. They're different tools for different purposes. Right? Now, when it comes to the HBase versus Cassandra, the tide seems to be swinging in favor of Cassandra. Those are the two biggest in that category, but Cassandra seems to be winning there. In the pure key value stores, it seems that Redis and Memcached are sort of winning the race there. Some of the others are lagging a bit behind. Mongo seems to have picked up the lion's share of the document store database. Neo4j and has picking up most of that category, and Solr and Elasticsearch are contenders for the search side of things. On the compute battles, it's decidedly less decided, if you'll pardon the repetition. The contention we're going to make is that Spark is a much better solution than traditional MapReduce, but that everything else is more or less up in the air. Right? There are use cases for Spark streaming, but there are use cases for Storm. Do you want to use Hive, Spark SQL, Impala? A lot of this is still very much up in the air. Okay, and this slide sort of, where did we get these figures? These figures come from DB Engines, right? The DB Engine rankings, and I have a link to this if anybody wants it. The DB Engine rankings They don't actually measure the number of installations of these systems so much as they use a series of different metrics. For instance, the number of times that a particular system is mentioned on a website. They look at Google Trends. They look at the frequency of technical discussions on Stack Overflow, DBA, Stack Exchange, those sorts of sites. They look at job listings, for example, on Indeed.com and Simply Hired. They look at the number of profiles on LinkedIn that mention a particular technology. They look at tweets. Okay, so they're sampling data across a number of different areas to try to determine which of these things is more popular than the other. So, as mentioned, the Redis seems to be winning by a very large margin, the pure key value store. You can see the number up here if you can read it. Their index for this, and the number is more or less an index, right? Their index for Redis is 95. Memcached is the next one, and that's 33. That's a pretty significant difference. The key document store, that's MongoDB by a rather wide margin. You can see that Mongo's index is 279. CouchDB is the next contender, and it's 28. Okay, so we're talking an order of magnitude preference for Mongo. Cassandra and HBase. Cassandra is still almost double in their index over HBase, but both of those are still contenders. Neo4j in the graph database is hands and away the winner in popularity. And of course, the term winner here doesn't mean necessarily best from a technical point of view for your needs. It's just this is what most people are using, right? I view this a lot like the old beta versus VHS debate. What wins is what's used. And then on the search side, you can see that Solr and Elasticsearch are pretty much the two winners there. So this is where the information comes from. So in general, these questions are more or less settled. Okay, so here what we're trying to talk about here is that you've got Hadoop and MapReduce, which was the original general batch system for big data processing. And then, along came this cloud here of a short period of specialized systems, all built to use MapReduce, all completely different from one another, and therefore you learn one and you got to start fresh when you're learning another one, right? So it's an ecosystem that is kind of fragmented both from a product perspective as well as an IT technical knowledge perspective. Right? I can't learn Giraffe and translate that knowledge directly to Storm or to GraphLab or any of the rest of these. They're all different. Right? So what Spark is trying to do is to kind of unify all of this stuff. Give you one unified API and approach for dealing with all of this information. So that you don't have to learn 15 or 20 different fragmented products to try to get the data through your processing to try to figure out what the heck you're doing. Because we're not here to learn data tools, right? We're here to process data. So if you have to spend less time learning the data processing tools, you can spend more time processing the data, which is the whole point. All right, and another contention that we will make is that, as a rule of thumb heuristic, 2 engineers who know the Spark API can now do what used to take a team of 10 engineers. Right? Why? Well, because the Spark API is unified. Right? You can connect it up to a bunch of different things, but it's all the same API. You spend a lot less time learning, a lot more time doing. All right, so this is basically the layout or the breakout of what Spark is providing. So it provides scheduling. It will schedule computational tasks to run in a cluster for you. It allows you to monitor the progress of your big data application. And this is true of Spark out of the box, as well as additional tools and add-on things like if you use the Databricks offering, there's even some more additional monitoring there. But Spark out of the box running on your Mac, you can connect to it and get all kinds of monitoring information. It also allows you to distribute computational tasks across the cluster, which we all sort of take for granted, but doing that cleanly and efficiently is part of what Spark's mission is as well. And as we'll see as we move forward, a lot of this stuff you kind of get for free. It just works. All right, this is a fun slide for some value of fun. Okay, so the big ball of red giant in here, I haven't decided whether this is a sun red giant or like the molten core of a planet. I haven't gotten an answer on what that is, but that represents Spark Core. Okay, and these icons, a lot of this is to introduce the layering, the onion, if you will, around Spark. But pay attention to the icons that we're using here because they're going to be used throughout the presentation as sort of markers to indicate what area of Spark that we're talking about. Okay, so these icons, obviously, if you can look closely, that's a disk. That is what a friend of mine calls spinning rust, right? So it's not an SSD. There's disk and memory, and so that's to indicate that Spark Core works off both disk and memory, right? A common contention is Spark has to use memory. No, it works off disk and memory. So that's where Spark Core comes in, and there are a variety of APIs that are built around that, such as the Data Frames API is built on top of Core to provide a faster and easier way to access your data. And then, as you can see here are the icons for Scala, Python, Java, and R, the interaction languages. They're all conceptually part of Core, but they're kind of sitting on top of the molten part of Core, if you want to think of it that way, right? Around the outside here, we've got add-on libraries. All of these are above the Core. They're not really part of Core. They use the facilities provided by Core to give you additional ways to interact with the data stream and to interact with Spark. So there's a SQL engine, right, that allows you to do SQL-type data queries. There's Spark Streaming, which again, as we'll talk about later in the day, Spark Streaming sits on top of Spark Core and basically translates streaming data into the Spark Core way of looking at the world. There's a machine learning library, MLlib. Again, that's around the outside of Core. It's built on top of Core. It depends on Core to get its work done. There's GraphX, which allows you to do graphing of your data very cleanly. BlinkDB, we'll talk about briefly. BlinkDB is kind of cool. It allows you to do approximate queries. Look, I don't care how accurate this is. I just want it fast, right? And then you can check the error confidence levels that come back from it to determine, okay, that was fast, but is it too fast? Is that, is this, I'm not real confident in this data. It's an add-on that's being rolled into Spark that I think is one of the cooler things that it provides. And then there are things like Tachyon that provide, some alternate ways to store this stuff. All right. Around the outside then, above all of that, is Mesos. We've got Mesos. That's obviously the Mesos logo at the bottom, right? That's a cluster manager. We've got Yarn. Everybody's familiar if you're with Yarn in the Hadoop environment. These things do work with Spark. The little gold laptop up at the top indicates standalone mode. This is mostly the mode that you tend to use when you're learning Spark on your local machine, right? You're simulating a cluster, but you don't really have a cluster. It's all being done locally inside one JVM. And then the flamingo standing on one leg is supposed to indicate standalone. Okay, this is another cluster manager. For instance, if you get the DataStax distribution that bundles Spark, that's the cluster manager that's built into the DataStax Cassandra offering. All right, and we will talk a little bit about all of those things as we go forward. All right, and then at the bottom, there's this little man, which is, it's hard to see, but that's supposed to be a zookeeper. Okay, so you can make the bottom three, not the standalone mode, but the true cluster managers, you can run them under Zookeeper to make them highly available, to do restarts, to do the redundancy that Zookeeper provides. They will all work within Zookeeper, provided you want to get your head inside Zookeeper. All right, and then around the outside is the rest of the ecosystem that can use Spark, or that Spark uses. So Spark communicates quite nicely with Hadoop HDFS, for instance. So those of you who have huge amounts of data in HDFS, none of that has to change. Spark will read from that and you won't even know the difference. Okay, it can interact with many of these different databases, right? So these are the NoSQL databases. You can read from or dump into these things using various adapters. So again, you can continue to use the data stores that you're familiar with. It will read any Hadoop input format. It can use things like Flume and Kafka to help you do buffering through streaming. All right, these are all built in, and there are various distributions of them as well. Okay, so you can roll your own, or you can use some of the distributions that are already out there. Right, and then in addition, there are your applications. Right, they're part of this large ecosystem. You're going to be building Spark applications, which use some or all of these features to get the data from one end to the other, right? So and they're not necessarily Mac apps, despite the logo, obviously. There are some applications out there as well that other people have written that you may use, but primarily we're going to be talking about apps that you write. Okay, we're not going to talk about this. This is just cute. All right, so the Spark team, the open source team that contributes to Apache Spark, there are developers on that team from more than 50 companies. Currently, more than 400 developers are contributing to it. Now, by developers, we mean people who are, for instance, issuing Git pull requests. Hey, I made a change. Can you guys put this in? And then we have, the team also has committers. These are the people who can say, oh yeah, that's a pretty good pull request. I think we'll pull that in. Okay, so 16 different organizations are involved in being able to authorize those sorts of things. The point of this slide is basically to say, by using Spark, you're not locking into a vendor. Right? This is an open source product. You are not necessarily required to buy into a particular vendor's way of doing things. Even though Databricks is sponsoring this, you're not even required to buy into their particular way of doing things. Spark is open source, and yet there are plenty of vendors out there that will help you support it. So I think that's kind of a good balance. All right, so this, the intent of this slide is to talk about what do people mean when they talk about Hadoop, right? So people say Hadoop, and they think that it means something, and really it doesn't mean just one thing, right? You can break it up into roughly 3 things. There's the MapReduce part of Hadoop. There's Yarn, which is the resource manager, and then there's Hadoop's distributed data store, the HDFS, right? All 3 of those are part of Hadoop, but they're somewhat distinct from one another. You can actually use HDFS without using MapReduce. And that's sort of where we're going with this, right? So the idea of the hard lines here are that these things are either equivalents or potential replacements. The idea of a dotted line is that they're not necessarily replacements, right? So in this particular case, we're going to make the argument that Spark is a better solution than using Hadoop MapReduce. But that doesn't mean you're throwing Hadoop away, all of Hadoop. You're basically, the idea is that you may find as you're using Spark that it's a lot easier to do the kind of things that you're traditionally doing in MapReduce, to do those in Spark. But you can do that without getting rid of Yarn, or if you prefer Mesos, you can continue to use that. It doesn't get rid of Yarn at all. Spark will work quite fine within Yarn. And you won't have to get rid of use of HDFS. Spark works quite nicely with HDFS. It's also worth pointing out that the Spark team is full of people who contributed very heavily to Hadoop. Right, so this isn't a bunch of Hadoop haters coming in and trying to kill the beast, right? They actually want people to be able to use the information that they have built up and stored in their Hadoop infrastructures, but to do so more easily and with less difficulty and with a unified API. Right, and then down here are a couple of other equivalences, right? So we've got Hive on the left, the flying bee elephant thing. Right, well, you can continue to use a lot of your Hive queries, but the contention that we're going to make is that Spark SQL is going to provide an easier way for you to do the same thing. All right, rather than using Mahout, you have the option of using MLlib, which again is built into Spark and built on top of Spark Core, and works quite nicely with all those components. You may choose to use, instead of Storm, Spark Streaming. Again, that doesn't mean there are no use cases left for Storm. And it doesn't mean that if you decide to use Spark Streaming, you immediately have to take all of your Storm-based stuff and translate it to Spark Streaming. There are plenty of places out there that are using both. All right, so part of the intent here is to get rid of some of the fear. A lot of people think, here comes somebody else. I've spent all these years learning Hadoop, learning how to do things with Hadoop, and now this new upstart is telling me I have to throw all of that away and learn something new yet again, and rebuild my entire infrastructure around something new. And those of us who've worked in enterprise, that's a big fear, right? You can't do that. You're never going to get a boss to buy into that, right? And the point here is that you don't have to. The point is that, yes, you may find that it's a good thing to transition away from Hadoop MapReduce, because it's hard and slow to get things done in that particular infrastructure, but you can move in that direction gradually, and you don't have to pull stuff out of all the data stores that you're currently using. You don't have to stop using the resource managers that you're using. It's something that is intended to fit within the existing ecosystem, so that those of us who've spent years building up these technology investments aren't suddenly forced to throw them all away and start fresh. Right? So you should all feel very comfortable that nobody is saying pick up all your Hadoop stuff and throw it out the window, because that's not what anybody is saying. All right, but here's the pitch as to why you want to try to move away from the map reduce part of Hadoop, as opposed to you can keep the rest of Hadoop, but why are we arguing that you want to use Spark over MapReduce? And this graphic is intended to sort of lay that out, right? So this is the kind of the chain of the way things tend to work with MapReduce, right? Your data is in HDFS, you pull it out into a batch job, and then it gets pushed back into HDFS. So there's plenty of disk I/O there, which tends to slow things down, right? And this process continues. And in fact, you may have a big loop in here where you've got a bunch of these things. Hey, I got a MapReduce job to do. Let me pull a bunch of data out of HDFS, run MapReduce on it, shove it back into HDFS. Let me do another one that pulls that data out of HDFS, runs another MapReduce job, and shoves it back in, which is why things like Oozie exist, right? Oozie is basically a task manager for this kind of thing. It allows you to, and the name was deliberate, right? Oozie's, we're shooting MapReduce jobs into the environment, right? But that basically allows you to set up a bunch of MapReduce jobs and cycle them in a particular order, or this one will fire if that one works. But the big problem here is that the amount of time you're spending rewriting stuff to and from disk all the time. So these things tend to be slow. By contrast, again, here we're pulling the same data out of HDFS, but much of it is as much of it as possible is being cached into memory being faster than disk. This will mean that Spark will tend to process this data faster because it's reading it out of memory instead of constantly persisting it back to disk. So multiple Spark jobs are going to run with cached in-memory data wherever possible. That doesn't mean that they can't use disk. It just means that they're going to prefer memory as much as possible, which will speed up your jobs. And again, this will be your loop strategy within Spark, right? You're not going to need Oozie. You can get Spark to do this for you. But the idea is that as you're transforming this data, you're not staging it back to disk all the time. So the throughput tends to be much, much faster, right? And then at the end, when you're finally done all this transformation, you can shove it back into, here we're shoving it into Cassandra. You could shove it back into HDFS for another job. You can even shove it back into HDFS because those guys over there haven't translated their MapReduce jobs yet, but we have. And so therefore, we're going to push it back into HDFS so their job can run tonight, right? But we're going to gloat and say, look, we got done so much faster and you guys are still working on yours, so you really want to come over to our side of the fence, right? Okay, so this is just to indicate the kind of work being done on Spark, right? There have been just over 17,000 commits made by 448 contributors, representing, now this is actually an old slide. This says representing 330-some thousand lines of code, but as we heard earlier on the first day of the summit, where the Spark is actually up to about 400,000 lines of code. Now, lest that make you nervous, oh my, the core is changing all the time. Most of these changes are actually in the libraries, right? The core is stable, which is not to say that the core is not being changed. It's being enhanced and it's being tuned, but it's essentially stable. So most of the bulk of these, the code changes being done right now are on things like the R interface streaming, things that add value without perturbing core. Most of it is written in Scala. There's some Java in there, the Databricks guys tell me, but most of the implementation of Spark is written in Scala. The code is very well commented, and we're actually going to show you how to go dig through the Spark code later. It can often be instructive for getting more information than you're going to find in the documentation. It has a code base with a very long source history, and it's maintained by a very large development team, and commits are all very stable. The COCOMO model was used to evaluate the amount of time used to develop Spark, and they came up with about an 88 staff years of effort to build this thing. First commit was actually not March 2010, but August 2009, and the most recent commit was just, well, this says 2 days ago. I'm betting there were commits last night, to be honest. Right, and here's a breakout of the languages. right underneath of here. So you can see the bulk of it is Scala, but of course there's Java in there as well. You know, what I've heard from some of the Spark guys is we do it in Scala unless it makes more sense to do it in Java. We're not shy about jumping into another language to implement this. Obviously, there's going to be some Python in there because there have to be adapters written so that you can use this thing from Python. And this up here shows the commit history, and everybody wonders what this big drop-off is, like right in mid-2011. Why did the lines of code suddenly drop so dramatically from close to 1 million down to, I'm not even sure what the scale here is, but significantly less than 1 million? And the answer is somebody had apparently checked a huge data file into the Git repository, okay? And somebody found that and removed it, and suddenly, boom, there's a lot less code in there. So the moral there is don't check data files into Git, right? Right, and you can see down here at the bottom, you've got the number of contributors to this thing has actually been rising over time, and not linearly, right? More than linearly. So the popularity among people, among contributors, kind of is paralleling the popularity in the general, usage side of things. All right, and then, there are various people who distribute Spark in various bundles, right? So here are some of them. You can use it within Cloudera and Hortonworks, MapR, IBM. Everybody saw the big announcement. If you haven't, go find yesterday's Wall Street Journal. There's a big talk about IBM is stepping behind this and partnering with Databricks. Oracle is actually using it. The DataStax folks, they're the ones who provide the Cassandra distribution that uses standalone clustering. Right? And then there are loads and loads of applications built around this. These are just some of the companies that are building stuff around Spark. So, and so what's the point of this? It's not bragging so much as to say, look, if you adopt this thing, it's not a flash in the pan. Right? There are loads of people, loads of companies, many of whom are rather large, like IBM and Oracle, who are making a bet on this technology. So those of us who are going to start using this with clients or with our, with our employers, you're in good company. It's not likely to go away tomorrow. All right, we're not going to spend much time on this, but the point here is basically this is a justification kind of the Spark way of doing things. If you look at these numbers, you can see how much faster it is to read data out of memory. Right? If you can put data in memory, you're going at much higher speed to the CPU. You can transform that data much more quickly because there's a lot lower latency trying to get the data into the CPU where it can be manipulated. If you go to disk, it's immediately significantly slower, even if you're using something like an SSD. The difference in throughput is dramatic, even with nice fast disks like the SSD that lets my Mac here boot in 5 seconds. Right? It's still never going to be as fast as memory. As soon as you have to go over the network, then the throughput drops even more. So, the locality of the data to where it's being processed and the ability to cache much of that data in memory, those are good things. And this is what Spark works very, very hard to do, to make the data go through the system that much faster. All right. I'm not going to spend time on this other than to say there are a number of slides in here that point to the original papers behind Spark. They're a little bit out of date compared to the current code base, but they're still worth reading. So if you've managed to get the Wi-Fi working and download a copy of the slides, it's worth going out to these links and reading these things in your spare time. So there are a number of them. There's a paper here on RDDs that's well worth reading. Right? There's a paper here on Spark streaming that's relatively new. There's a comment at the bottom here that the 2 streaming papers have been cited over, 138 times. Again, if you want to get some background on Spark streaming from a slightly more academic perspective, there are papers out there. They're readily accessible. They're not behind a paywall. That's the important part. You can go read them anytime you want. There are papers out there on Spark SQL. How does this work? How does it interact with Hive? How does it make your life easier? Why is it a good thing? Papers on GraphX. And then a whole bunch of stuff on BlinkDB. And again, I'm not going to spend too much time on this, but here's the cool thing about it. Imagine being able to do this. Look, I want to get data from this table within 2 seconds. In other words, I don't want to wait any longer than 2 seconds for this data set to come back, even if it's inaccurate. Right? And here's another one. I want to get a certain amount of data coming back. I would like it I will wait as long as I have to wait, as long as the confidence level for this data is 95%. Right, so you have ways of querying this information and deciding how long do I want to wait, how accurate do I have to be. Sometimes it's good to get an approximation of the answer fast, as opposed to a 100% accurate answer if you have to wait an hour. Right, and that's what BlinkDB is providing. Right, and then how do you know if you're doing this and you're repeatedly querying this data? Okay, I've gotten an approximation. Right, I'm going to try back later, and if there's more data in there, maybe I'll get a more accurate answer. And how do you know when to stop querying? If you're always getting back approximations of the information, how do you know when it's okay to stop and move on and do something with this data? And the answer is that BlinkDB returns error bars. So you always get confidence levels back with a query, so you can always say, all right, I've reached a point now where I'm confident enough. All I really wanted was 85% confidence. I'm there now. I can move on. I think this is a pretty exciting thing. All right, and then finally, for those of you learning Spark, if you have not bought this book, run right out and buy it right now. Okay, it's an excellent book. I have a copy of it in my backpack. I carry it around with me so much that it's already getting dog-eared because I'm stuffing it into corners of the backpack, even though I have no room in there. So carry this with you. Read it more than once. It's not very big. It's not very expensive. It's definitely worth having. And apparently it's fairly cheap right now on Amazon, 30 bucks. Okay, finally, a couple of things about information of Spark, on Spark, where you can find stuff about Spark out on the web. Okay, so obviously spark.apache.org is the base website. Loads of really good documentation out there, in addition to the book, which again, go buy. There are mailing lists out there, so if you have questions that you can't get answers for, you can always go to the mailing list. Although personally, I find rather than use mailing lists, my first recourse is generally Stack Overflow. So there's a Spark tag out there for Stack Overflow, and as befits most of what's on Stack Overflow, there are loads of really good answers out there. So don't hesitate to just go out and look for Spark under Stack Overflow as well. In addition, there's this relatively new package index for Spark. I guess the best way to describe this is it's, for those of you in the Java community, it's kind of sort of like Maven Central or Bintray's JCenter, although it's a little bit better than that. For those of you from the Python community, it's a lot more like the Python package index, PyPy, right? It's basically a repository of third-party Spark tools that people are building around the ecosystem and making available to other people. One advantage that this has over something as simple as Maven Central is that there are ratings. I don't know if you can see them there, but there are some stars, right? So, hey, this looks interesting, but is it any good? Well, what do the ratings say? How many people have rated this? What are the star ratings on this? What are people saying about it? So this is not only a place where you can go out and get stuff and download it and install it within your Spark ecosystem, but you can evaluate it. Is this useful for my needs? Do other people like this thing? Right? And this is only going to grow. So this is out there as well. Spark.packages.org is the link for that. So go out and play around with that. It's relatively new, as you can see by the big new icon up there at the top. Okay, now this we're going to, and don't worry, we're going to get to some code soon. All right. The intent here is to talk about the preconception that a lot of people have that Spark requires memory, right? Well, that's really good. Spark's really fast, but if your data set does not fit in memory, you don't want to use Spark, right? That's not going to work. And that's actually not even remotely true. So there's a sort competition out there, the 2014 Daytona sort competition. The intent here is to sort 100 terabytes of data. I don't know about you, but I know of no machine that has 100 terabytes of memory, right? So there's no way you can accomplish this task all in memory. So the question then is, if Spark only works well if you can load data, all of the data into memory, then Spark should do very poorly in this sort of a test. And in fact, it beat the crap out of most everybody else. Certainly beat Hadoop in this case. So you can see this table in here. The only thing I'm going to talk about are the top few of these, right? So the data size, Hadoop MapReduce, example of this, about 102 terabytes. So roughly on par with Spark, 100 terabytes, right? Took Hadoop 72 minutes and 2,100 nodes and 50,400 individual physical cores to get that done in 72 minutes. Spark did roughly the same amount of data in almost a third the time, right? It's 23 minutes. It used an order of magnitude fewer nodes, fewer physical nodes, and almost an order of magnitude fewer cores, right? And they were virtualized cores, right? They weren't even physical cores. And it still managed to complete the job in 23 minutes, all right? So anybody who tells you that Spark requires that all your data fits in memory, they may not intentionally be lying to you, but at the very least they're misinformed, because that's obviously this data shows that that's not true. And then later on, a team of Spark engineers decided, can we do a petabyte? So you can see here what they managed to do, how quickly they managed to process a petabyte. Took 234 minutes, only used 190 individual nodes, and used even fewer cores, but roughly the same amount of cores, in the order of 6,000 virtualized cores to get this job done. Right, now that was actually a very interesting test, because it tended to completely, the CPU and the network tended to be a bottleneck there. But even with those things being a bottleneck, it still took only 234 minutes to do a petabyte of data. I think that's pretty impressive. And that puts the lie to any claim that if you don't have a lot of memory, Spark will perform poorly. That's just not true. Okay, and here's some news on that. Feel free to go out and look this stuff up. All right, and then finally, why is the sorting thing a particularly good test? It's challenging because you're not reducing the data, you're not filtering anything out, right? You're just reordering the existing data. You're not reducing the data set at all. Sorting tends to stress shuffling, by which we mean data has to move across the network so that it's moved to where the other nodes are sorting similar data, right? And so, if you're sorting 100 terabytes, the example that they saw was it's about 500 terabytes of disk I/O, 200 terabyte network. Okay, so sorting is a good stressor for this kind of thing. There's additional information out on here if you're interested in it, including, and I'm not going to go through this at all, but there's some physical information about the machines that were used to do this job, if you're interested. Information on the infrastructure used, how large was each record, what version of the JDK was being used, what version of HDFS. This was actually Apache Spark 1.2. Wouldn't surprise me at all. Now that we're up to 1.4 and soon 1.5, if this could be done significantly faster. But there's more information here, and you can find more information about these tests out on the web. All right, and then finally, if you like what you see with Spark and you want to take some of this training home with you, if you go out to the Databricks.com site under Spark training, you can request training that's on site that you don't have to go to a conference to get. All right, so Databricks is expanding their training offerings dramatically. That's one of the reasons that I'm here and others are doing this. So training is available. You don't have to just learn this on your own. Okay, now that we've done all the background stuff, we're actually going to start digging into some of the more technical aspects of Spark. Right, and we will eventually get to where you're putting some code in yourself. But we have to do some background first. Okay, so the first thing that we're going to start talking about are RDDs. Okay, so what is an RDD? It's a resilient distributed data set, and we're going to talk about what that means for a few minutes. All right, now, if you have ever installed Spark locally, you will have seen something like this. This is an interactive shell. Okay, you'll often hear this referred to as a REPL. Hands up if you've never heard the term REPL before. Okay, I guess I should explain what it means then. It's just a fancy programmer term for interactive shell, right? But it's actually an acronym. It stands for read, evaluate, print, and loop, okay? And it originally came from, of all things, Lisp. The idea, though, is that plenty of languages have these things. The idea is that you can key in commands, and they're evaluated right when you type them in. You immediately get back, that's the E part, right? So it reads a command from you, typing it in interactively. It evaluates it immediately, prints the result, whatever that is, if there is one, and then loops back and gets more out of you. Those of you who are used to Unix shells, and there are enough people with as much gray hair as I do that at least some of you have used Unix shells, that is, in a sense, a REPL. Okay, a shell is a REPL. Why do I say that? Because you can do more than type commands in there. Those of us who've used Unix for 30 years are used to typing for loops on the fly in a shell, right? That's evaluating a construct that's not just running a command. So a shell is a primitive form of a REPL, all right? Languages like Python and Ruby have popularized the REPLs. The idea that you can just type Python and you're immediately, instead of running a program, you're sitting there in a command shell. And now you can just type Python commands. And the REPL will know where the end of the statement is, and when you hit return, it runs it, and it shows you the output. Ruby has one. Scala has one, which was quite challenging for them to implement because Scala is actually a compiled language, right? But the Scala REPL allows you to get inside one of these interactive shells and type Scala code, and it runs it right then and there and shows you the output. Okay, so that's the purpose of a REPL. Now, why do we bring this up? Well, we can talk about this later, but I always like to talk a little bit about these things, and REPL is the way people say it, right? So if you hear me say REPL, it's because I'm a programmer and I'm so used to saying REPL, and it's faster than saying interactive shell all the time. But a REPL is a fantastic way to experiment, okay? If you're in a language that does not have one, such as Java, how do you try something out? Hey, I've got this third-party package and I want to see how it behaves and how the API works. You write a test program, which you then have to compile and you then have to run, right? So the overhead is a little bit higher. REPLs also tend to provide you, good ones tend to provide things like tab completion, right? What methods can I call on this thing? Well, I hit the dot, hit a tab, and there they are. They're right there. So it's a great exploration mechanism. So the Spark REPL is currently provided in two flavors, right? There's the Python version of it, and then there's the Spark shell, which is a Scala version of it. These are essentially, think of them as the stock REPLs for those languages. So the Python REPL, or IPython if you're a Python guy and you like that, and the Scala REPL, but they're preloaded with a bunch of Spark stuff. So the entire Spark ecosystem is there for importing, and you have some predefined variables that are automatically connected to the local Spark cluster or the local mode. So they immediately give you the ability to just start playing with Spark right there. Just type stuff in, see how it works. You want to load a file up? Load a file up. All right, so I will encourage you. Now, we're not going to use the REPL in here because we're going to use the one that's out in the cloud, right? We're going to use the Databricks notebooks, which have built-in REPLs. But when you're doing stuff on your own, get used to using the REPL. It's a great way to experiment with this stuff. And if you're like me, you'll start to get frustrated that Java doesn't have one yet. Apparently, there's one coming. I just hope it doesn't take as long as Lambdas. Okay, so the first thing to think about with Spark is this idea of a driver program, okay? So the driver is essentially what's running your application. So when you bring up the REPL is actually a driver, all right? And what it does is it connects to the Spark cluster. There are ways to make the driver highly available, and we can talk about that offline. You can use that in Yarn as well to make these things quite highly available. But the thing to remember is that the REPL is essentially a stand-in for your application. And it's starting everything up or making the connections. In a cluster mode, the REPL is actually communicating with the nodes in the cluster. So the REPL or the driver is going to push work out to these clusters. Okay, and I'm not going to go too deeply into what these little boxes are in the clusters, other than to say they're individual JVMs that are capable of receiving and executing work. We'll talk in more detail about what those things actually are and what I mean when I say they're JVMs capable of receiving work. We'll drill into that a little bit more deeply later. But this happens even within the REPL, and that's the point. If you have a cluster running, you can bring the REPL up and tell it, I'd like to use this cluster, and it will do the exact same thing that any normal Spark application will do, which is to push that work out into the cluster and then bring it back for you. Now, by default, you can still use the REPL even if you don't have a cluster. By default, it comes up and it simulates a cluster by using the JVM it's running in. So it's essentially, you can think about it analogously to, it's not using a cluster, it's kind of using a thread pool, right? A local thread pool to run the work. So obviously you're not going to want to do heavy duty work that way, but it's ideal for playing around with Spark, because now you don't have to worry about, well, I can't even start to play with this thing until I bring up a cluster. And the answer is that's not true. You just bring up the REPL, and right there you're in local mode. And you can play with Spark, and no, it's not going to be as fast as if it runs on a cluster, but you can do all the things you can normally do and see how they behave. So what is an RDD? An RDD is an abstraction, okay? It is a representation of data. That data may or may not be local to your machine. That data is broken up into partitions, okay? So the general idea is that if it's distributed around the cluster, those partitions may or may not be local to the machine where the driver is running. But the RDD itself, consider that to be, think about it sort of like a collection. Okay, so if you're used to using collections APIs in Java, just out of curiosity, how many people in here have done any work with Java 8? Okay, you guys are at a slight advantage. Okay, because if you've looked at the Java 8 collections API and the Lambda capabilities in that language, a lot of what we're going to talk about will seem very familiar to you. All right, so it's the same general idea. Think of the RDD as sort of like a distributed collection. Whether it's really distributed or not depends on how your cluster is architected and whether you're running in local mode or not, but think of it as a distributed collection. All right, and you can do collection-y things on it. The more partitions you have, the more parallelism you are likely to get. So the more that you break up the data into partitions, the more you can spread it around the cluster. Okay, now this is an example. Consider that we have, notice that this RDD, which again, this is an abstraction, right? This is a handle to a hunk of data, which may or may not all be local, right? When you run it within a 3-node cluster like this, these partitions are going to be distributed around the cluster. So here we can see that the first partition has been moved over to this first node. All the transforms, all of the things that we do to this data will be done on that node with that partition's worth of data. This partition may be allocated to the second one. And by the way, I'm not like outlining any kind of partitioning algorithm here. This is the kind of thing that may happen. How this stuff gets distributed, don't rely on this diagram as any sort of reference. This is pure illustration, right? The third one and fourth ones and fifth ones may end up distributed like that. Okay, so we have 5 partitions and only 3 nodes. It's not possible for each partition to end up on its own node because there are fewer nodes than there are partitions. So by definition, at a bare minimum, some of the nodes are going to be working on at least 2 of the partitions. Okay, is that clear? All right, so now we have one with 4 partitions instead of 5. This is supposed to look like kind of a representation of a log file. So this is actually a fairly common thing that we need big data tools to deal with. I've got a log file that's a full terabyte of data, and I have to drill through that log file and look for certain kinds of errors, right? And with a traditional program, reading that 1 terabyte of data is going to take a long time. So we're going to try to use some sort of a distributed processing mechanism to get through that data faster. So we take the log file, we create an RDD that's broken up into 4 partitions. So you can see that in this, in this theoretical approach, or this theoretical example here, we have an RDD on the left here. There's a line in there with error in it. There's one with warning in it. There's one with error in it, right? The second partition doesn't have any error information in there at all. The third partition has some error information. The fourth one does. Okay, so once again, these things are going to be distributed out for processing. So now there are actually 2 ways to create an RDD. You can read data from an external source. That's the second bullet here. So you can read data from S3. That's fairly common, actually. You can read data from, for instance, Cassandra or HDFS. Right? This is what you're doing in production usually. For testing, though, you do not necessarily need to have an HDFS setup that you're reading from. You don't necessarily need to have anything in S3 or Cassandra. If you're playing around with Spark, you can have it read a text file, you can have it read a JSON file, or you can even say, look, I just want to see how this thing behaves. I've got an array of 10,000 elements that I just built here, or even 3 elements. You can take that array and you can tell the REPL, you can tell Spark, look, parallelize this. All right? And this is where the Java 8 guys will have an advantage, because this is something you can do with the Java collection in Java 8. You can say, I want to make this collection parallelizable. right? When I teach a Java 8 course, one of the things I like to show people is what happens if you sort an in-memory collection of 10 million items as a standard sort. You know, bring up top or your performance monitor and watch the cores, right? And then what happens if you do that same sort and parallelize it? And I like to watch all the cores in my system peg when I do that. It's kind of fun, right? Nerdy fun, but fun. So this is sort of the same kind of thing. For the purposes of playing around with Spark, you do not need to have some sort of an external collection. You can just take an array, parallelize it, and now that splits that array up into partitions and gives you an RDD, and you can play with it. Obviously, not suitable for production because it implies that all your data is in memory, and we've just said that that's not a reasonable thing to assume or rely on when you're dealing with big data. But when you're playing with Spark, the goal here is you want to be able to learn how to do this stuff without having to have a huge amount of overhead setting things up. I don't want to have to make sure I have access to HDFS or S3 or some enormous file just to try to learn the API. You don't have to. You can just take an array of data and parallelize it, and now you can do all the normal Spark stuff on it. Okay, so here's how you can parallelize something. Can everybody read that? Maybe it's my resolution. I can barely read it. So there's this SC variable. We're going to see this a lot. When you bring up a REPL, everything is done in Spark, starting with a Spark context. Okay, if you're writing an application, you have to create one of these things, but in the REPL, you get one for free. So the top line is the Python REPL. Okay, and we have this Spark context already built for us called SC, and we can parallelize it by calling a parallelize method on the Spark context, passing in an array of whatever we want, a list in Python terms. And what we get out of that is an RDD. It is a representation of that same data partitioned and ready to be spread out across whatever cluster you're working with or whatever threads are available in local mode, depending on how you're running the REPL. Right? And you can see examples of the same thing in Scala. It's a little more verbose, but not as much, not as much as Java. And at the bottom, you can see the Java version, right, where we have to put a type in there. Right, so notice now the reason we don't, for those of you who don't know Scala, the reason that we don't put a type in the middle one where we just say val is that Scala does type inference. So it is strongly typed like Java, but it can infer the type, which means that in a Scala REPL, you have to type less. That's, those of us who like Scala, that's one of the things we like about it. I don't have to type as much. Okay, but you can still do this in Java, and you can see at the bottom an example of that. It works in all of these languages. All right, so again, just to summarize, it takes an in-memory data structure, an in-memory collection, a collection that's native to the language. So a list in Python, a list or a sequence or a set or something like that in Java or in Scala, right? And it passes it to the Spark context parallelize method, and gives you back an RDD that has split it across partitions for you to play with. Right? And as I mentioned before, you can read from a text file. So instead of saying sc.parallelize, you can say sc.text file. All right? I like to play with this using the dictionary, the spell check dictionary on the Unix or Mac system, usually under user shared dict words, right? That's a fairly large file of words, one per line. But pretty much any file you can open up. And what this does is it partitions the contents of the file and produces an RDD for you. Partitions it by default in lines. So you notice here we're saying sc.text file. Okay, we get a lines RDD. So the file is broken up into individual lines, and then those lines are allocated to partitions. So each partition is going to have some number of lines. And now you've got a distributed view of that text file. Right? Turns out there are other ones too. You can have it read a JSON file. We'll see examples of that later on. I find those to be really, really useful for testing. There are also ways to read things like a CSV file. Usually you need a third-party add-on of some kind for that in Java, like OpenCSV. In Python, of course, you can just use the built-in CSV reader. But the point is, and I'm not showing you how to do that, but the point is that it's really trivial to load these things in. Right? And then there are other methods to read data from HDFS, Cassandra, S3, HBase, other data sources. But for you guys, when you're starting out playing with these RDDs in the REPL, just use a text file. You know, if you're done parallelized, just get some relatively large text file. So here's our log file, right? Back to the log file example. Normally, the first thing that we create, the first RDD that we create in any particular application or within the REPL, there's a term that the documentation will use to refer to that RDD. The first RDD you create, we generally call either the input RDD or the base RDD. You'll see both. From what I've read in the documentation, the terminology seems to be migrating towards saying base RDD, but you'll still see input RDD. Just think of that as, this is the first RDD, this is the start of where I'm going to do my work. Okay, so this thing represents the entire input data split up into partitions. And represents is the key point here. You'll note the dotted lines around this. Nothing has been loaded yet. So when I do this, nothing is loaded into memory yet. No data has been read from that file. The partitions have been allocated. The algorithms that decide how to distribute the individual lines of this text file, for instance, across those partitions have been prepared. You know, they're there. We know how we're going to partition it under the covers, but it isn't actually read into memory. You are not opening a file here. It's analogous to a file open, but you're not even really opening a file. In a sense, you're saying, look, I intend to be working with this data, but don't read it in yet. Okay? What we're introducing here is the notion that this stuff is lazy. Okay? It's lazy in the sense that, and again, those of you with Java 8 experience, this is not a new thing if you played with the collections. The idea is that we're going to be building up the lists of things, the transformations, the operations that we want to perform on this data, but we're not going to do any of it until the end when we say, okay, go get it. Go do it. We're going to talk about that a little bit more. Right? So here's an example where the log file is actually in HBase. Okay, and so the little green block icons are deliberately chosen to be blocks because by default, what happens is that the HBase blocks, each of those becomes a partition. Okay, they're assigned one-to-one to a partition. But again, note the dotted lines. It's sort of like saying, hey, this is where I'm going to read from, but we haven't read anything yet. Just by connecting to an HBase data source doesn't mean you've read anything. Now the red line, and that's, we're going to have to clean this icon up. That's supposed to be like Optimus Prime or whatever. It's a transformer, okay? So this is supposed to denote, and I mention that because you're going to see that icon numerous times here. Essentially, we're breaking up, think about the operations, the actions, the things that you can do on an RDD. We can roughly break them up into two things, transformations and actions, all right? Those are just terms, so what do those terms mean? A transformation is something I'm doing to the data. I'm either taking pieces of the data out, I'm transforming the data into another representation, I'm converting it to some other format. That's a transformation. An action is essentially boils down to retrieval of the data. And in Spark, actions are what trigger this stuff to finally run. All right? And I'll get to what I mean by that in a little bit. So here we're calling filter on this RDD. What we're intending to do is remove data from the RDD that we're not interested in. All right? Or keep data we are interested in. So in this particular example, I'm looking for errors. So what am I trying to do? Filter anything out that is not an error. I'm only interested in the records that have errors in them, and so I'm going to apply a filter transformation to this thing. What do I get out of that? I get another RDD. Now, this is a bit misleading because this is the view of these RDDs as if the data were in there, but there's no data in here yet. We are building up basically a set of instructions at this point to Spark. Spark has still not read a single piece of information out of the file. What it has done is it's building internally a set of instructions, a set of operations that it will perform later when we apply an action. So now this first RDD, the instructions associated with that first RDD are you're going to read out of HBase. The instructions of that in the errors RDD, the second RDD, essentially is both sets of instructions, right? It's sort of, think of it as the path, right? The path starts with a read from HBase and then runs through a filter operation. So somewhere captured inside that second RDD is a set of instructions that says, this is what you're going to do, but we haven't done any of it yet. Hence the dotted, that's what the dotted lines mean. Nothing has been done yet. In the Spark documentation, when we actually do stuff, when the data actually starts flowing, the documentation tends to refer to that as materializing the RDD. Nothing has been materialized yet. There's no data that's been pulled into memory yet at all. We are building up an internal list of instructions about things that will be done later. Okay? Right? And then maybe we're going to start again with this errors RDD. So this is just, think of this as a continuation, right? And then maybe we're going to apply another transformation, right? Which is a coalesce. What is coalesce? Coalesce basically says, look, notice that one of the partitions is empty now. Why is it empty? Because that particular partition is full of data, never had any error stuff in it, right? So maybe I want to reduce the number of partitions. I'm kind of wasting some resources here. We'll talk later about how you can determine that information, right? But at the moment, just take it for granted, there are ways to determine that, hey, you know, I'm kind of over partitioned here. So I'd like to reduce the number of partitions I'm using. So coalesce is another transform. This basically says, okay, at this point, I want another RDD that only uses 2 partitions. We're going to call this the cleaned RDD. Note the dotted lines. We still haven't read any data. We've assembled a list of instructions. At this point, those list of instructions are start by reading HBase, all right? Then filter the partitions that come in from HBase so that I only have error information in them, get rid of all the lines that aren't error lines, and then drop down to 2 partitions. Okay, that's the set of instructions. Turns out internally, we'll see in a minute what they use internally, but it doesn't really matter. Just think of it as a set of instructions that will be executed at some point. Here's the point. The green arrow is, green was chosen because green is for go, right? This is what's going to kick the whole thing off. This is not a transformation, this is an action, right? And that's this, by again, going back to Java 8, for those of you who played with that, this is how the parallel collections work there as well, right? This action is collect. Note the little action clipboard there, right? Collect basically says, okay, hey, cleaned RDD, I want you to go get the data. Collect, I'd like a collection, a native collection of the data in the cleaned RDD. At that point, the data starts flowing, right? So the actual read occurs at that point. The data is read from HBase, it flows through into the first RDD, the first filter transformation is applied to it, which pulls it down into the errors RDD. The coalesce pulls it down into 2 partitions, and finally the data that's sitting in the cleaned RDD flows into our application and gets stored in a native collection. Normally collect returns something like an array or a list, depending on the language that you're using, all right? So at this point, we refer to these RDDs as being materialized. Okay, the data suddenly materializes out of the data store, flows through the application, and comes back into the driver. Okay? So whether it was run in local mode, at which point it was always in the driver JVM, or run out on the network and distributed across a series of clusters, the point is that this final collect pulls all that data in and into the driver JVM, which in the case of the REPL is the REPL itself. Now, the next question is, what happens to the data at that point in those RDDs? Anybody want to take a guess? It's gone. The pipes are now empty, okay? It's all gone. It flowed through the system, dropped into our JVM or our application through the collect operation, and now they're all empty again. Now you can reuse them. We could take the cleaned RDD later on and run another action on it, presuming it's still in memory and hasn't been garbage collected, or I could run another collect on it. There are a number of different actions. We'll look at some of the actions later. But I could call any other action on that later. Count is another good example, right? Having pulled that data into a collection, I could also run count on it, which is kind of silly because I've already got the collection in memory. I would typically call size on that. But if I were just playing around, I could take the cleaned RDD again, call count on that. That's another action. That starts the whole process up again. HBase is opened up again. The information flows once again into the top level RDD, flows down through the filter, flows down into the cleaned RDD again, and then it's counted and the answer is given back to me. Okay, so by default, that's what happens. They are reusable, but at the moment, nothing is stashed anywhere. So every time you call an action on this cleaned RDD, you're starting that whole process all over again. All right, now this has, that's supposed to look like, I guess, a fuse being lit, all right? The term that's used, remember I said we're collecting these instructions internally and we're executing those instructions. So when you call collect, the instructions are finally executed. Read from HBase, run the filter, run the coalesce, give me the information. That's all done finally when you call the action. The only reason that I'm mentioning the term DAG in here is that you will see that term in the documentation. It's an implementation detail. It turns out that that list of instructions is internally represented as a directed acyclic graph, hence the term DAG. Okay? In an ideal world, you wouldn't know that and wouldn't care. We would just call it list of instructions, but it's made its way into the documentation. So you will see the term DAG, and those of you with a strong computer science graph background know what it means. It's a directed acyclic graph. You don't need to know that to use Spark. You don't have to care. When you see DAG, it's just the list of buffered up instructions about things that we're going to do that get executed. Okay? That's what the term, from a usage standpoint, that's all it means. All right? And what happens is that when you call one of these actions, the directed graph gets walked. Right? And it's directed because direction implies ordering, right? So it's walked in order, and those transformations are applied, and then you get to the end and you run the action. Okay? But if you see the term DAG, that's all it means. Okay, so this is another representation of the same thing. The idea here, notice, what do you note here? Notice that the driver has called collect, and suddenly the boxes get not dotted anymore. Okay, that's a notation we're going to use in here to mean that the RDD has been materialized. Okay, it is now actually doing something. There is now actually data flowing into this RDD. Okay, so in this particular, as we move forward, if you see hard lines like this as opposed to dotted lines, that means data is flowing. The pipe is being filled up. Right? So all of these guys, we run through a filter, the filter operation, the data is now flowing into the errors RDD and flowing into the cleaned RDD, right? And then passed into the collect filter where it goes into the driver, right? And then when it's done, and this is just, we'll talk about stages later. We're not going to talk very much about stages at all, but if you run across stage in the documentation, it essentially means this collection of operations being done. We will talk in more detail about this later. But the idea is, as I said, once you've collected the data, all these guys go back to not being materialized. Hence the dotted lines. So here's a more interesting thing. Remember, I talked about this. You can call actions on these guys as much as you want. So here I have the cleaned RDD. I could choose to save to Cassandra. So once again, I've started the pipe running, and as the data comes into the cleaned RDD, it gets shoved into Cassandra. I can do a count on it. I mentioned that one earlier. Note that I can also add additional filters to this. You can call an action on any RDD. Doing so does not mean you can't also later filter that RDD and make yet another RDD. So what happens here is that there's a certain DAG, a certain list of instructions associated with the cleaned RDD, right? And if you call save to Cassandra, it runs that set of instructions. If you call count, it runs that set of instructions. If you add another RDD, okay, so we're looking, this is called error message 1 RDD. Presumably, maybe we're filtering for particular error messages. I'm only interested in error messages that are related to this particular virtual host, if this is like an Apache log, right? So this second RDD down here at the bottom, the error message 1 RDD, that has a larger DAG, right? It's the collection of instructions that you see for up to the cleaned RDD, But then another step, another filter tacked on that is now the DAG or the set of instructions for error message 1 RDD. Calling an action on an RDD does not mean you cannot use that RDD to filter and do other transformations on later. Okay? These can be combined like little integrated circuits, right? Tied together however you want. Now there is something kind of wasteful going on in here, right? Presumably, once I've gotten this enormous log file through the log lines RDD and the errors RDD and boiled down into the cleaned RDD, that's essentially the data set I want to work with from now on, right? And I might want to work with that in a number of different ways, as shown here. I might want to dump a copy of it to Cassandra, get a count of the information in it, do some further filtering on it. Each one of those operations is going to reread once again from HBase and start the whole process again, which is slow and kind of wasteful. So let's assume that I've put my filters together in such a way that by the time I get down to the cleaned RDD, I've really winnowed the data set down. Right? It's now been boiled down to the smallest pieces of information for me to work with, and there's a very good chance that that's going to fit in memory. So what can I do? Wouldn't it be nice if I could, it's fine if the log lines RDD drains, and it's fine if the errors RDD drains, but I'd really like to keep the information in that cleaned RDD around in memory if I can, so that I can call collect on it, and then call count on it, and not start the whole reread process all over again. And you can do that. This is supposed to indicate it's that you've called a cache operation on this RDD. So once you've created the cleaned RDD, you can call a cache operation on that. And that effectively says, look, when you do the read on this thing, keep it around, cache it. Don't go back to HBase for it, keep it here. And by the way, you don't have to know ahead of time, will all of this data fit in memory? The cache will persist out or spool out to disk. There are a number of different caching strategies we can look at later. But by default, it can be set up so that it will spool it out to disk. The point is, it's still better to do that than have to go back to HBase and get it and process that whole huge amount all over again, right? You've already boiled it down to a much smaller amount of data. Even if you have to reread it from disk, it's a smaller amount of data. It's still going to be faster. Yes?
Can you specify a timer for the cache?
Can you set an expiration time? I'm not aware of one. There may be a way to do that. In general, it'll go away when you throw the RDD away, though, right? So you could just, if you want to make it go away, you could throw the RDD away and just create a new version of it. I mean, the point is that these things are supposed to live long enough for you to do transformations on them. They're not typically going to live, for days, right? All right, so here's the general life cycle. This is sort of a recap. The life cycle of a Spark program. Create some input RDDs from some sort of data. If we're doing this in production, it's almost invariably going to be some sort of an external data source, like HDFS or a big file or something, right? Or an S3, a big file sitting in an S3 bucket somewhere. But if you're just playing around and trying to understand some stuff, it's fine just to parallelize a collection. Lazily transform them to define new RDDs using transformations. Transformations are lazy. So this is a key thing, and I'm going to mention over and over again. Transformations are lazy. They don't do any work until you run an action later on. This is the stuff that builds up that DAG, that set of instructions. Okay, you can do as many transformations as you want, and no work gets done while you've applied the transformation. The work finally gets done later on in step 4. Later on in step 3, after you've applied all the transformations, when you get down to the minimum data set that you want to work with, the bottom RDD, if you want to think of it that way, you can choose to cache that, which then means I'm saving a much smaller part of the data set that I want to work with, so that I don't constantly have to rerun the whole set of instructions and reread from the huge data source again. And then finally, once you have, whether you do step 3 or not, finally you're going to launch certain actions which will extract information out of there. Maybe pull all the data in, maybe just count it, maybe save it to some other location like a text file or a Cassandra data store. Right? So this is it, really. I mean, this is the basics. It's as simple as this. And it really is this simple. So here are some of the transformations. This is not all of them, and I'm not going to go through all of them. This is supposed to give you just a flavor of some of the kinds of things, the lazy transformations you can apply. You'll want to look at the documentation or the Learning Spark book to get a fuller list. But this is the sort of thing that you can do. There's map, there's flat map. I will describe flat map later. There's a very easy use case for flat map, but we're not going to talk about it right now. Filter, which we've already seen. You can do things like distinct, intersection, the coalesce that we've already seen. You can do set style unions. There's a whole bunch of things that you can do here that are all still lazy. They don't do anything until an action is called. All right? And here are examples of some of the actions. Again, this is not all of them. This is just some of the more common ones. Okay, reduce. Reduce is an action that, for instance, I've got a numbers of pieces of data, and I want to reduce those pieces of data down to ultimately one thing, or some series of one things. A good example of this is the classic hello world example for Spark and for this kind of thing is a word count. Right? I've got some huge data source and I want to count the number of distinct occurrences of a particular words in this thing. That's a reduction operation, right? You're not keeping around the words, you're reducing them down to the word and its count. Okay, so you use reduce operations to do that. Collect, count, we've already seen those. Give me the first element out of the collection. Take the first 10 elements out of the collection. There are a whole bunch of these. Take a random sampling of the elements out there. Save this stuff someplace like a text file or Cassandra or some other kind of thing. There are loads of these, and again, you want to take a look at the documentation to see all of them. But those are examples of some of the more popular actions. RDDs are typed. I'm not going to spend much of any time on this at all, other than to say that the underlying implementation language, Scala and mostly, and then some Java, these things are all stored in strongly typed different kinds of RDDs. Why do you care about that? Most of the time you don't, except that if you know, for instance, that you're transforming an RDD of single items into what's known as a pair RDD, for instance, a key value pair, right? Well, if you've made a pair RDD, then if you know the type of the thing, now you can go look and see what additional operations are available when you're operating on pairs of objects as opposed to single objects. And my typical way of doing that is I'll get in the REPL and I'll say, okay, I've created this RDD, what is it? Okay, the equivalent of a Java get class, what am I looking at? Or in Python using a type on it. What do I have? That tells me where to go look in the documentation for this thing so I can see the list of methods that are available and look at what they do. Okay, that's really the only reason we care about typing here, is that different RDDs have different capabilities. So knowing what kind of RDD you're dealing with tells you what kind of operations are available on the data stored inside of it. Okay, and then finally, as I mentioned earlier, if you're reading the documentation for a particular RDD, either at spark.apache.org or in some other place where you found documentation, maybe inside the book, and you're not satisfied with the amount of information that is in there, then you can always, as they say, UTSL, right? Use the source, Luke, right? Go out to the GitHub repository, find the RDD that you're looking for, and there are ways to search in GitHub, right? So figure out what it is that you have in your hand. Go find the source code for that thing in the GitHub repository, and it's github.com/apache/spark, okay? And then pull it up. And even if you can't read Scala, that's okay. What you're looking for are the comments. These things are highly, highly commented, very well commented. So there may be some additional information inside the source files that didn't make its way into the published documentation that can help you understand a few things. All right, so it's not necessary to read the code per se, but there's loads of docs in these things, so don't be afraid to go look at the source code. It's all out there for your perusal. Okay, so these two slides are just pointing to it. This is a list of all the existing RDDs in Spark Core. Okay, so you have a copy of these slides. You could go out to this GitHub repository yourself and dig through these things. Right? Now, this is in here not because Alan Kay is cool, but though he kind of is, but because this quote of his is sort of what the Databricks guys have adopted as a kind of a motto. or a mission statement, right? Simple things ought to be simple to do, right? You shouldn't have to do a huge amount of setup just to accomplish some simple task. Complicated things might require more work, but they should still be possible. So this is the idea behind Spark, right? Most of the work you're going to be doing is simple, straightforward transformations and collections. They should be easy to do. You shouldn't have to do a huge amount of work just to do a simple transform. When you start to have to do some really complicated things, does the API support that stuff? And the answer is yes, it does. You may have to do some more work, but the point here is that the standard simple use cases ought not to be hard for you to do, but when you've got to get into doing something more complicated, the primitives are still there for you to do it, even if you have to dig a little deeper. All right, so that's sort of the philosophy behind building this stuff out. All right, so at this point, we're going to take a look at the Databricks user interface. All right, and then after we do that, we're going to take another brief break so that I'm going to basically give you guys, we're going to open the doors and let you guys get in and play with this. But we're going to also take a break about that time just in case we run into some network issues. That gives us a chance to, as you're trying to get into these things, if there's a problem, we can use the break time to help resolve that problem as well. But first, before I let you guys get in there and start playing with this, we're going to walk through a little bit of this. It's kind of necessary because we want you guys to understand how this actually works. So in order to do that, I want to come off. The off of here and go over to Chrome. So give me just a second to pull up the pieces that we need. All right. I think this one will work fine. All right, so presumably everybody can see this, right? So what we're going to look at first in here.
Brian, can you use Apple Plus to make
You want to make this
text
larger?
quite a
That's
bit larger?
fine. Okay. How's that? More
Yeah,
readable?
that's great.
Okay. So when you first log in, what you're going to see is this Home tab. Sorry, I Apple Plused my instructions over here, which is not good. Right, and I highly recommend in your off time, don't do it in here, please, but in your off time, go through these 3 videos here. Each one is just a few minutes long, well worth it. We just don't want you streaming them down over the Wi-Fi for obvious reasons. But they're very good. They're very, Andy, are you the voice on these? It sounded like you when I was listening to these.
Yeah,
things.
that's me.
Yeah, that's what I thought. So the guy back here is the guy who's actually walking you through these videos. They're very good. They give you a real good sense of how the flow works within here. Now, we're going to walk through a little bit of that here. Okay?
Are they going to expire, like our username and password?
Eventually they will, but you'll have, I think it's a week access to these
Will
things.
you repeat all questions?
Okay, so the question is, when we give you access to the Databricks UI, will your logins expire? And the answer is eventually they will, I believe.
That's correct.
I think it's a week.
Right.
Right, so what happens is, and we're going to talk about this a little bit, we've got clusters allocated for each of you. They're not extremely large, but they're there. Okay, now those are going to go away fairly quickly because they use up resources on EC2, right? But there will be a large one called a community cluster that after these classes are over and your individual clusters go away, you can still play in here for like a week. And you'll be able to use the community cluster to do that. The only downside is that if you're looking at any of the UIs, your jobs will be intermingled with everybody else's, right? So when it comes to trying to figure out what's going on, looking at some of the diagnostic APIs, it might not be very clear what your stuff is, but you'll still be able to play with this stuff for a week. Also, you can always just create your own account on Databricks.
And all notebooks can be exported as source and then re-imported into any other tool that you're using, like an IPython notebook or something, if you choose not to go with Databricks.
Right, we're actually going to do that. I'll show you how to export a notebook. You can pull down the source. The other thing is that if you were to choose, if you like this tool so much you wanted to create your own Databricks account and you did that, you could go back here and export your notebook in a format that is easily re-imported into, sorry about the noise back here. You can easily take one of these things and basically drop it down into a file and reload it up into another area, another shard, we call it, and you get an exact copy of it. In fact, we were doing this last night because we have 2 different areas for you guys to log into, and if I made a change to something in one, I had to do exactly that, drop it down into an export, and then import it into the other one. This is really, really easy to do. Okay, so this is the home slide. Basically, from here, always use this thing over here. Okay, and there are a number of things in here to talk about. All right, workspace is where we're going to spend most of our time. Right, and the first, let's look at clusters first. These are the clusters that are out there. Okay, each of these clusters out here is one cluster per individual. All right. And please, when you'll know which cluster is yours, please use only your cluster. They're not big enough to run that you really want multiple people using multiple clusters. Okay? If you have your own one of these, if you've signed up for your own account, you can add new clusters. You can see I have an add cluster button up here. I can make a new cluster. You will not be able to do that because you would be using Databricks resources, and of course that would be bad, right? But I mean, as an admin of your own area, you can create clusters, you can kill clusters, you can restart them. All right, and you can create different kinds of clusters. How much memory do you want the thing to have? Whether or not it uses Amazon Spot instances. If you don't know what that is, don't worry about it. You give clusters names, you know, and it's automatically creating them for you and creating the appropriate EC2 nodes. So basically, bottom line, if you wanted to create one of your own, all you really have to have is an Amazon AWS account. And as soon as you have one of those and you've given Amazon your credit card, you're good to go, right? As long as you're chewing up your money and not Databricks, you can do whatever you want. All right, you won't be doing much with these other than making sure you use the right one today. You can look at tables. We're not going to spend much time looking at that right now. This is where we're going to be spending our time. Now, one thing to be aware of is the Databricks guide. This is very good. You can make clones of these things if you want to play with. There are examples inside the Databricks guide. One of the nice things about these are called notebooks, right? This is a folder. Folders can contain subfolders. Individual folders have notebooks. This is an example of a notebook. Basically, a notebook, think of a notebook as documentation intermingled with REPL sessions. Okay? So some of them have REPL, some of them don't. This is a great thing to be using. This is a REPL session. I can run this. Okay, right now I can't run it because it's locked. But you could make a clone of this and put this inside your folder. And now you have a copy of the Databricks notebook. You can play with it, you can attach it to a shard, and as you're walking through the documentation, any place you see something that looks like a REPL, you can execute that code and see how it behaves. And then of course you can modify it in line. Right? So to execute it, which you can't see here, but it always shows up on the screen, you type in code, hit return as often as you want, then when you want to execute it, shift return. Boom, it executes on the cluster. Okay, really, really easy to use. So if you need to clone it, and I recommend that you clone the Databricks guide and haul it in so you can play with it at your leisure. Basically, you just do clone, and it comes up, and you currently have to type the full path to your folder in here. I think one of the future enhancements will be like a picker that will make this easier. So you have to know where your notebook is. Your notebooks are all going to be under home, so it'll be /home/ whatever your student number is, which I believe is all of you have this probably on the back of your badge. All right, we'll get to that in a little bit. All right, so for the moment, if you leaped ahead and figured out how to log in here, please don't. We'll do that in a little bit. What I don't want you doing is playing while we're talking. I want to give you the overview first, right? And then you get to play. That's the idea. Don't play now, right? Because if you play now, you'll waste time. All right. So in home, your individual cluster. I'm sorry, your individual folder will be under here. Once you have a folder, it'll be empty, but you can copy other people's notebooks in here, provided you can see them. You can also create a new folder, a new dashboard, a new notebook. This is the thing you'll be doing more often than not, creating a new notebook. So you could create a new notebook, and inside that notebook you can put stuff, okay? And you can just create, you can run SQL commands, you can run Python commands, if you choose a Python REPL or notebook, notice that if I wanted to create a new notebook, I'm not going to do this because this is one of the student areas, but notice that you can choose a Python notebook, a Scala notebook, or a SQL notebook. So whichever language you want to use to interact, you can choose that. Now, I will point out that if you choose a Python or a Scala notebook, you're not prevented from doing SQL. There is a way to do SQL even if you have a Python notebook or a Scala notebook. Okay. So I generally choose Scala because I'm a Scala programmer, but I'm also happy with Python. I teach a Python class. I'm very familiar with Python, so sometimes I'll choose a Python one. They essentially work the same way. It's just that the language you're using to interact with Spark is different. Okay. And again, the other nice thing about this, as compared to a REPL, if you think about a standard REPL that you've pulled up, the Spark shell or IPython, history is saved, but your entire session is not necessarily saved, right? And you can't really annotate what you're doing with documentation. It turns out it's really easy to throw documentation in here. We're not going to spend time right now doing that, but you'd be able to see it when you walk through the labs. There's basically a way within any notebook to put Markdown. If you're familiar with Markdown, you know it's a lightweight markup language. GitHub uses it, right? You can intersperse inside your REPL, you can intersperse Markdown, which is why when you pull up the Databricks guide, that's why you get all this fanciness here, right? Basically, this is Markdown. And it's automatically rendered the same way GitHub renders a readme.md, right? Why is this useful? Because it means if you've gone to the trouble of building out one of these sessions and you think this is useful for your coworkers, you can now intersperse documentation in there. Or as we do, we build training out of here. What's a lab? It's a bit of Markdown that tells you what to do and a bit of REPL stuff that you can run, and then other areas where you can plug in additional REPL areas where you can put it in your own code. Okay, it's really useful that way. And again, you can pull this all down as source code and run it inside like Python or Scala at any given point. Underneath here, we have our labs. So when I tell you to do a lab, the lab will be under here. What you will notice is that the labs are all locked. Why are they locked? Because I don't want you modifying my labs. Okay, so when I tell you to run a lab, I'm going to say to you, look, you got to clone this lab into your environment. Then you will get, and then what you will need to do is associate that with a particular cluster. So let me show you what that means. This is my instructor folder, okay, and I've got copies of stuff in here, all right, and some S3 credentials there, which I've locked so you can't see those. Notice up here in this particular notebook, this is one of the labs. You'll do this lab later on. There's some REPL stuff in here that can be run. Okay, so I can go into here and I can say, now this is a Python notebook. How do I know? Because there's no val in front of the base RDD. But since this is unlocked and it's attached to a cluster, I can actually run this. Okay, so that ran the cluster. That ran the sc.txt file out on the cluster. It didn't load that file. It said, look, I want to load that file later. Okay, when I materialize this RDD, that's what I want you to read. And it stored the RDD in this particular variable. Shift-Enter is what did that on the cluster. This does not work if you're not attached to a cluster. So if I detach this, okay, now I'm not attached to a cluster. If I go over here and I try to hit Shift-Enter, notice what it does up here. Okay, you can't run this, you're not attached to a cluster. So what you're going to do is whenever you run a lab or whenever you create a new notebook or decide to play within here, you need to attach to your cluster or you won't be able to run anything. Okay? So that's the key abiding principle here if you're using this in the class or if you decide down the road to make your own. You can't do anything unless you're attached to a cluster. What this means for you down the road is if you make your own, if you decide, sure, I'll pony up some of my Amazon money to create one of these things, it means that before you can actually do anything in a notebook, you have to create a cluster. So you have to go back over to here and actually create a cluster. So why don't you get one for free? Well, because clusters run on EC2 and they're not going to give away free CPU time, right? You have to pay for your CPU time on EC2. So it's up to you to create a cluster if you're the administrator for a particular Databricks account. But you can control how big that cluster is, how much memory it is. And everybody knows that Amazon instances, you could sit in here for 3 hours playing with this, running against an Amazon cluster you created, and you're probably it's only going to cost you a few bucks, right? So, I mean, and Amazon doesn't charge a monthly fee, so I have an S3, I have an EC2, an S3 instance myself, and per month it doesn't cost me much of anything. But it's nice to have it, because if I want to play in here, now I have something I could hook up to this. Okay, so that's essentially how this kind of works. There is a collaborative capability in here, right? I can have you come into my cluster if you want. So if you look inside the Databricks guide, you'll notice I'm not the only one in here. Okay? More than one person can be in a particular notebook at one time. If the notebook is unlocked, it means that more than one person can be typing in that notebook, sort of the same way two people can type into a Google Doc. So it's collaborative in that sense. It's a useful way to work. We actually saw, and if some of you may have seen, some of the Databricks guys do this during the conference, right? They're giving a talk and they're using this. And I forget who did it, but one guy was giving a talk and then he had Matei come in and say, look, correct me as I do this. And you could see Matei making snarky comments in there as he's working through it. So that kind of collaboration makes this very easy to use. It's hard to share a REPL, but it's easy to share one of these things. So that's useful to know. Okay, and then finally, we're going to do, let's take a look really quickly. A couple other things that you can do in here, and I will do that from here, where I have a runnable one. Okay, let me pull up. Let's pull up this one. All right, so again, I come in here, it's loading right now, that's why it took so long. I can't do anything in here, it's detached. So I'm going to connect to a cluster. Now I'm going to connect to one I would prefer that you don't connect to right now. Use your cluster, but later on, here's the community cluster. Okay, this is the cluster that you will have access to after 5:30 today for about a week, that you can all run against for free for about a week. I have my own mini cluster down here called the Instructor mini cluster, which is configured identically to the clusters you have. So I'm going to connect to that one so that I make sure that I'm under the same constraints that you are. Right? So now it's attached and now I can do things. What if I want to save this and load it into a new cluster or save it as source? How do I export this thing? Turns out it's pretty easy. You go back here, there's a drop down right next to the file. I can rename it if I don't like the name it got. When you clone something, by default, the word copy ends up on the end of it. You can change the name. I can lock it. What does that do? That means nobody can modify it. That's particularly useful to do if you have a cluster that's connecting to S3 and you have your S3 credentials in there. You don't want people being able to open up and look at them. The nice thing about this is any individual area of the REPL can be closed. Okay, so I can define a whole bunch of commands inside a REPL window, and then I can minimize that. It minimizes down to a little window. Once I've done that, if I lock the notebook, nobody can go into that notebook and open that up again. Which means if I've got a notebook out there that has my S3 credentials in there that I'm going to be using to make connections, I can leave that notebook out there, but I can minimize portions of it, lock the notebook. You can read everything else in that notebook, but you can't open that up and look at my S3 credentials. So that's a useful feature. I'll show you how to close one of those up in a minute. But it's useful to know how to lock a notebook. I'm done with this. You guys can read this, you can clone it and fool around with it, but you're not going to modify my copy. Clone is the thing I showed you before. Make a copy of it, copy it someplace else. Export is the one that we want to look at here. And I'm not sure where that just went. I think I have a screen issue going on here. Let's try this again. Oh, it's off screen here. So let's do this. Let's roll this over a little bit here. So export has a submenu. You can export it as a source file, which means it could be, if this were a Python notebook, it could be run through Python, right? Or IPython. A DBC archive, that's basically a native format for Databricks. So the idea is if you export it as a DBC archive, you can then import it into another Databricks shard, and it comes in, and it's just like a native storage format that preserves everything as is. Now, of course, it won't preserve the cluster assignment because presumably you're doing this to take it over to another shard, and the clusters may all be different, but it will capture everything up, and it gets loaded back in to Databricks exactly as is. Right now, you don't have control over the name of that thing coming down. They all come down as, I think, databricks.dbc, but that's a future enhancement as well, so that you don't end up with, 1, 2, 3, 4 of those in your, and not know which one's which. All right, so that's basically this overview. By the way, you can delete a notebook at any time in here if you're done with it. You just get rid of it. All right, let me see what else we want to go over here with really quickly here. Oh, okay. We're not going to spend a lot of time on this right now. We'll look into this stuff a little bit later. But in any given notebook, let's go to this guy. In any given notebook, another thing that's up in here is the Spark UI. Right, and this gives you information about the stuff that's been running on the cluster and the jobs that have been running. All right, and this is the thing I was saying. Once your individual shard goes away and you use the community cluster, if everybody is using the community cluster, your stuff's going to be intermixed in here. Now, I wouldn't worry too much about the UI right now. We're actually going to go through this in much greater detail later on, but it is there, okay? And one of the tabs that's really useful is this storage one. If you cache an RDD, you'll see it reflected in here. Okay, this RDD exists and it's been stored. All right. Beyond that, I don't want to spend too much time in there. I'm not going to spend any time in tables yet. We'll see that more later on when we talk about data frames and SQL. So essentially, that's a brief overview of the UI. I think we've covered pretty much everything I want to cover. Andy, is there something else in here you think we should cover?
Nope. I think we should take a quick break and just reconvene quickly. So we're going to have lunch in about 45 minutes. So we can take a 5-minute break now. There is coffee out here if people need to recharge for that. And then actually, yeah, it's upstairs. There are sodas just outside the door. Yeah.
Right. So when we come back, whenever you come back, I guess if you trickle in, you can start to play with with this. Are we ready to do that, or do you guys want to check some stuff first?
No, they should all be able to log in. Everybody can try logging in now over this break.
Right. So during the break, let me go back to here really quickly. Some of you, I notice, have already done this, which is kind of cheating.
I think like 90% of the room's already in.
Right. But if you're not in, and I've got to find the slide now that I've restarted this. If you're not already in, then where you want to go, it's way down here. I forget the slide number. I lost my place. Okay, hang on. Here. This slide tells you where you are. Basically, you've got usernames and passwords on the back of your badge. If you're user 1000 through 1980, you're going to be in class East 01. If you're, this actually is wrong. Your back of your badge tells you which cluster? Okay. So it tells you which cluster you're on. It tells you your ID. It tells you your password. This is how you map the cluster to a URL. So just connect, log in, and what I would suggest before doing anything is clone the Databricks guide into your area.
And if you have any issues, come and talk to one of us.